sources, that is LED. LED we have started. Anyway, I will take that concept again since that will comes under the sources. Okay, so you can see, is it my screen is visible to all?
Yes, sir.
Yeah, thank you. Uh, for second internal, sorry, the second internal, we have completed up to 29 lectures. You can see from 30th lectures onward, we have started. I have given explanation on what is meant by optical communication, what is the need of the optical communication, and we have seen different types of optical fibers. Okay, 31, sorry, 30, 31, then 33, sorry, 33 we have to go. In today's class, 34 we going to complete. The 32 I will take. Okay, 32 is a ray theory and mode theory. So, and the step index and the graded index is over. Okay, we are going one by one, and most probably we will complete this content soon. And after that, we have some revisions. Okay, and we have some frequently asked MCQs, and please get through with all. Anyway, even then, you not have the questions for first internal, second internal, third internal. I will make a soft copy on that and I will put it into the Google Classroom as a question bank. And along with that, some other frequently asked questions also I will give. Before the end semester exam, you have a practice on it and you can get benefit for your end semester exam. Okay. Okay, students, today's class is on the numerical aperture. That is, you can see this thing. There is a two cases I have provided. The two rectangular shape is there. So, what is this rectangular shape? So, suddenly, if I show this image to you, what do you think? It is one geometry, rectangular figure, but not. Okay, so since we are deal with the optical fiber, in optical fiber, how many layers are there totally? There are three layers are there. What are the layers? Core, cladding, and protecting sheet. Okay, core, cladding, and protecting sheet. So just remember like a PCC or CCP, like that. Core, cladding, and protecting sheet. So this is nothing but your core part. This rectangular shape is the core part. So when the signal bend over at the top to bottom or bottom to top, so how this effect can be taken? Okay, so when the you can see the statement has been given like this: when the light crosses the interface boundary into the medium with a higher refractive index, then light bend towards the normal. Okay, so what they're telling means this is your higher region. Okay, this is your higher region. Whenever the signal having a bending property, that is called as the refraction. Okay, refraction, there is a two terms are there, reflection and a refraction. So reflection is nothing but I will show in diagrammatically so that you can you have studied in your physics concept. Okay, like yeah. So if the light signal is passed on this medium and it will be reflect on the same medium, then this is called as the reflection. Okay, then it is called as the reflection. If it is bending over on the other medium is called as the refraction. Okay, so whenever the refraction is occur, then the this refractive index will be induced in that medium. Refractive index will be uh, induced in that medium. So that is what they are telling. When the light crosses that interface into the boundary into medium with a higher refractive index, then the light bends normal. That is, light bends normal. So the best example is that in a glass of water, pure glass, you can that is a normal glass. Okay, not a steel glass, mirror glass. That is mirror glass. You can take pour water and put a spoon. or a straw, and you can see in the side. You can see that even the material is in linear. When you look, it will be look like a broken path. Okay, so that is the best example of this refraction. So the light traveling across an interface from higher to the lower, the light will bend away from the normal. This is the statement given in optic communication. Okay, so regarding in optical, it will be given like this. So this property has some critical angles. So what is the critical angle? That bending only I am telling. If the incident light hit the interface at any angle larger than the critical angle, that is phi I is greater than that of phi c, the light will not passes through the second medium at all. So you can see that glass. Okay, so even then it is a linear. You have some critical angle on it. So the visibility when it goes, it will be look like that. So that is the reality also. So whenever the wave is propagate on the medium, some signal will go in linear, okay, which is normal to that medium, and some will bend and produce some refraction or reflection. Instead of all, it will be reflected back to the first medium. So this process is entirely called as total internal reflection loss, TIR. Simply they will call it as TIR. Okay, like FIR, TIR. Okay, total internal reflection loss. Due to this property only, maybe some interference, small interference will be occur in this optical fiber compared to the other medium. Actually, this derivation is very important before pandemic. Actually, in physical class, this type of derivation they will usually ask in the descriptive type. Okay, just actually, as I told, please see this condition. As per this condition, please see the light. I am underlining the light will be refracted at 90 degree. In other word, the refracted along the interface. Okay, this statement is given like this: the light traveling from a medium with a higher to a medium of lower, then the light will be reflected at 90 degree. That is this condition. So what only in this condition we are putting 90 degree. Actually, this equation, particular equation, is nothing but the Snell's law. So you may hear about the Snell's law. So no need of the full derivation. Okay, so this time. Okay, so just the formula. Okay, Snell's law. S N E L S. Snell's law. Okay, Snell's law. So the by Snell's law, you can see N1 and N2. N1 is the refractive index of the first medium. N2 is nothing but the refractive index of the second medium. Okay. Um, um, then sine phi 2 divided by sine phi. Okay. So at this condition, a numerator we are putting 90 degree. So sine 90 is nothing but 1. Okay. So if I am putting like this and simplify this expression, I will get sine phi c is equal to n2 divided by n1. This expression I will get. So by using this, we can find out the numerical aperture. So you may ask what is meant by numerical aperture. Okay. So in this diagram, we have shown only the small part of the reflection and the refraction. But please imagine if it is 100 kilometer optical fiber is there. In that, how this type of propagation has been taken place, like reflection and refraction. There are many. Okay, so that is called as the numerical aperture. So where aperture is nothing but the surface of the medium. So in that medium, how much it is occur numerically. Okay, so you can see here also some small diagram I have given. So this boundary, this inside boundary is nothing but the core. This outer boundary I'm drawing in different color. that is nothing but your cladding. Okay, so this is your cladding. So the shaded part in green color is the cladding, where inside to the red line is the core. In that core medium only the signal is propagating. Okay, so in terms of light. Okay, so that means whatever electrical signal is going on now, now please imagine, now my signal is electrical only. Okay, so now my signal is electrical. So I'm having my headphone, and I'm having the speaker and the mic. Okay, and also I'm having mic in the my webcam. Okay, and also in system is there. I have connected. So initially, how my signal? It is in electrical only. When it is transmitting, it may go in further processing. Maybe since it is transmitting through the base stations only. Okay, definitely it will be converted into photonics manner. Okay, it is like a radiation. In a fraction of second, even some delay is there in my signal, some small delay only there. So some people in Kerala, some people in Andhra, some people in other states, and some people in Tamil Nadu, but far away from me, but everyone getting my signal. How? What is the medium we are getting? If I ask means you will tell in my system, that is my medium, you will tell. So my system and your system are the entity. Okay, entities. So my point is the first point, and my signal is transmitting to all. Okay, all 32 students. Maybe some delay. I am not object with that point. I have some delay due to some bandwidth or the network issue. Some delay will be there, but definitely all will get my signal. Okay, so through the free space in backend. Okay, this is going in safety, that is in optic fiber cable. Okay, so definitely this signal not have that much interference, that much noisy. Okay, we are initial point itself, we are making some initial setup like I'm not have soundy place, that is noisy place. I'm not taking the class. Okay, I'm into some calm room and I'm taking class, so there is no additive noise will be added in your place, in your system. So you are receiving my signal. Okay, so in this case, we are going to see some characteristic parameter of optic fiber in the core, the core medium. You can see the relationship between the acceptance angle and the refractive index. So, what is the acceptance angle and the refractive index? So, the refractive index will induce whenever the refraction will come. What is the accepting angle? What is the accepting angle? So I will tell one best example for the accepting angle. When you going for any of the that is you are going for uh, that is mm, some museum you are going. Okay, you are going for one museum center. So when you get in for the museum center, you have to take a ticket. Okay, you have to take a ticket, and the ticket you have to give it to the counter man, and then only he will accept, and he will allow to get in. Correct. So that is accepting angle is also like that. In optical fiber, the opening will be there. So the signal should get penetrate on that optic fiber. So when it on that the starting point, it induces some angle called as accepting angle. Okay, so it is followed for the further medium like core, cladding, and the air. So the core is the inside. So then how come it comes for cladding and the air? Okay, so suppose you are in one building. Okay, you are in one building during the summer time. Okay, so in my home there are three buildings, three floors are there. So ground floor, middle floor, and top floor. Okay, Definitely at top floor, we have the heavy radiation so that we feel the heat. We will feel the heat. Whereas in middle, we will feel very less than the top, and in ground floor, we not have that much effect. Definitely, even then the signal is passing through the core. Some heat energy is propagating on the cladding and the top layer. Okay, so even these two are the protecting cladding and the protecting sheet or the protecting medium. Some energy will be disappear, like a heat energy. Okay, and some acceptance. Sorry, the condition has been given like this. Please see the incident on the fiber core at an angle theta 1 to the fiber axis, which is less than that of the acceptance angle. That is theta 1 less than theta a. Okay. The light may enter the fiber from medium axis of the refractive index. Fiber core has the refractive index which is slightly greater than cladding, and by Snell's law. You can see by Snell's law. So there is a two values are there like a n sine theta 1 and n sine theta 2. These two are equal, I'm telling. Why? When the energy is going inside the medium, fiber medium, the two angles are equal, I'm saying, by Snell's law. So this is applied in the Snell's law equations only. So don't get into it briefly. Just know the resultant equation. Then it is fine. Okay. And this is one part of the equation you should remember. This equation is nothing but the incident angle should be converted into the critical angle. Just remember the equation. Maybe during your that is gate exams, definitely it will be useful. So this equation is this condition. Okay, that is when theta 1 equal to theta a and pi equal to, that is, this is your critical angle condition. This is your incident angle condition. Okay, when you applying in the Snell's law equation, you will getting this condition. The incident angle should be converted into critical angle from the ray theory. So still we not completed ray theory, but I will tell what is meant by ray theory lightly right now. Actually, you have heard about the Raman's scattering principle. So what is scattering? So now I am doing the scattering. How? My signal is going to the medium. If some of the obstacles like birds are flying, big buildings are there, and due to heavy rain, okay, my signal will go or bombard with that obstacle, and it will be get returned back. Okay, that is called as the ray theory. In ray theory, there are different cases are there. When I'm taking ray theory, I will detailedly tell about the ray theory. But just simply remember, ray is nothing but the signal is going outside to the medium. Okay, so when it hit on the any of the obstacle, it will be returned back. So you can remember like this: when you are running very fast, okay, you not know you are going very drastic speed, okay, and if you are hitting on any one of the big man, you will fell down. If you hit on the small people will fall down. So like that only. So here we whenever we hit on to the bigger obstacle, definitely it will return back. If it is a small part, means it will go forward only. Okay, so this is the conditions. So when further they are calculating, so they obtaining the numerical aperture expression. So this is nothing but your numerical aperture expression. This you should remember. So no need of full derivation. At least you should remember this equation. That is numerical aperture. It is simply given as Na, and the refractive index of air medium is always 1. Sometimes in your 1 mark question they will ask the refractive index of air medium is 1. Okay, and numerical aperture. So what only this n naught becomes. So you can see in ninth equation, n naught is there. This is nothing but your refractive index of air. Okay, so sine theta max is equal to whole root of n1 square minus n2 square. So or otherwise you can put like n1 square minus n2 square whole to the power 1 by 2. Okay, so this is nothing but your numerical aperture expression. This also you can relate in terms of this refractive uh, difference between the core and the cladding. It is denoted by the symbol delta. Okay, there is a two formula for the numerical aperture. So you can see in before slide. This is in terms of refractive index. Okay, this is in terms of refractive index, where this is this equation. Okay, this equation is based on the refractive difference. Okay, refractive index is different, refractive difference is different. Okay, of between the core and the cladding. So twice of delta whole to the power 1 by 2 into n1. So this numerical aperture relation is very useful to measure light collecting ability of the particle. Okay, so this is the thing alone you can see. So don't look into the full derivation. Just look into this part for your um, um, for preparing. Okay, so I hope this concept is fine for you. Once again, I will shortly complete this process entire thing. First, we have started with one medium for refraction. Reflection is occur in the same medium. Then we have come up with the condition like 90 degree. If the light will be reflected at 90 degree, then the total internal reflection loss will be occurred. This process, entire process. Okay, and then we have given a relationship between phi c. It is a critical angle and the refractive index. So by using the Snell's law, just remember n1 divided by n2 equal to sine theta 2 divided by sine theta c, or 2 you can mention more. But the condition we provided like incident is 90 degree. So sine theta, sine 90 degree is 1. We have obtained this relation. Okay, after that we are applying this condition to numerical aperture for how the light is gathering capability in your core medium. Okay, for that we have given the conditions for it, and how the acceptance angle and the refractive index will be there. And we have provided again the two condition by using Snell's law, like theta 2 equal to theta phi 2, and also we have given phi is equal to phi c. Then we have obtained this critical condition like this, and we got this expression, seventh equation. Okay, then after we have applied the refractive index of air equal to 1, and then we have got this expression. This expression is nothing but numerical aperture in terms of refractive index, and at last we have get a refractive difference. By using refractive difference, we have obtained there is a revised numerical aperture. So you should remember both the numerical aperture value for the problems. So we go with some problems in the next class. Um, maybe after completing the theoretical concept. So I hope this concept is fine. If you're having any doubts or clarification, you can ask me at the end of the session after your attendance.